Modern text-to-SQL systems often start with a daunting checklist. Set up a vector database, configure embedding pipelines, and constantly re-index as your schema evolves. But is all this complexity really necessary? Many developers, including myself, have grown frustrated with the static nature of these traditional approaches. They treat database information as something frozen in time, relying on pre-embedded, pre-indexed data. Yet, when a human analyst faces an unfamiliar database, they don't just read documentation, they explore, run test queries, and interact with the data. This disconnect between how humans and machines approach databases sparked my curiosity. Could AI learn to explore databases actively, just like an expert analyst? Instead of relying on vector databases and embeddings, I wanted to teach AI to explore databases in a more human-like way. That's when I discovered the SDE-SQL, Self-Driven Exploration SQL research paper. The core idea is refreshingly simple. Let the language model actively query the database using targeted SQL probes before generating the final SQL statement. This approach allows the AI to learn about the structure, data distribution, and relationships within the database, all by asking questions directly. No more complex infrastructure, just SQL, exploring SQL. I decided to build this system and see how it performed in practice. SQL probes are like reconnaissance missions for your database. Instead of guessing based on semantic similarity, the language model sends small targeted queries to gather information before attempting the main operation. Think of it as the AI asking the database a series of smart questions to understand its contents and structure. This method leverages the database's natural strength, answering queries quickly and precisely. By using SQL itself as the exploration tool, we eliminate the need for embedding pipelines and vector indices, making the system both simpler and more adaptable. The SDE-SQL framework uses a tree-based strategy to break down natural language queries. First, it identifies what you want to retrieve the target, like a column in the select clause. Then, it figures out the conditions, such as filters or groupings. The process starts at the root with a base SQL probe to check if the target data exists. From there, it branches out, testing individual conditions and their possible values. Each path from root to leaf represents a specific condition probe, ensuring thorough exploration without overwhelming the system with too many combinations. This structured approach helps the AI understand even complex queries step by step. Let's see how condition probes work in practice. Suppose you want to find films with a PG rating. The system starts with a base probe to check if the rating column exists. Then, it branches out to test different conditions, an exact match for PG, an alternate format like PG-13, and even partial matches using SQL's like operator. Each branch is a targeted probe, and together they cover all possible ways the data might be stored. This method ensures the AI doesn't miss relevant results due to formatting differences or data inconsistencies. After testing individual conditions, the system combines them to verify that they work together. For example, it might check for films with a PG rating and a rental duration greater than 5 days. Each combination probe returns real data, informing the next step. This dynamic process allows the AI to adapt to the specific database it's querying, ensuring that the final SQL statement is both accurate and relevant. By systematically exploring all relevant paths, the system avoids the pitfalls of static, pre-embedded approaches. To put this approach to the test, I built a full-stack implementation using the popular DVD rental database. The backend runs on FastAPI with Python, PostgreSQL, and OpenAI's GPT-4, while the frontend uses React and TypeScript for real-time updates. The architecture features a 4-stage pipeline: schema linking, exploration, generation, and refinement. Real-time trace visualization and background processing make it easy to follow each step as the AI explores and generates SQL queries. This setup proves that you don't need vector databases or embedding pipelines to achieve high accuracy. The SDE-SQL pipeline is designed for clarity and efficiency. It starts with schema linking, where the AI extracts entities and values from the user's question. Next comes exploration, where SQL probes gather information about the data. In the generation stage, the system creates multiple candidate SQL statements and uses majority voting to select the best one. Finally, if errors occur, The refinement stage decomposes the SQL and explores alternative solutions. This structured process ensures that each query is handled methodically, maximizing both accuracy and adaptability. Instead of traditional vector embeddings, I used locality-sensitive hashing, LSH, for value retrieval. LSH offers several advantages. It's local, fast, and deterministic, with no API costs or external dependencies. It performs exact character-level similarity checks, works offline, and handles typos or case variations with ease. Unlike embeddings, which require expensive API calls and infrastructure, LSH provides instant, reliable matches. This makes the system more efficient and cost-effective, especially for projects where speed and simplicity matter. Let's walk through a real example. Suppose you want to find the phone number of a customer named Thomas Hardy from the UK. The system first extracts the target and conditions, then selects the relevant columns. It runs a series of probes, checking if the phone column exists, testing for the exact name, and verifying the country. Finally, it combines all conditions to ensure they work together. The result? The correct phone number is returned in just a few seconds, with high confidence and no need for refinement. The system also excels with more complex queries. For example, when asked to find a customer's phone number with multiple conditions, the SDE approach uses window functions and creates CTE tables as needed. The process follows the same pattern: schema linking, exploration with probes, and generation of the final SQL. Even with intricate requirements, the system produces valid, accurate queries by actively exploring the database structure and data relationships. How does this approach perform in practice? On average, a query takes about 6.4 seconds from start to finish. The cost per query is around $0.40, which is higher than traditional RAG systems, but delivers about 15% better accuracy. For simple queries, the success rate is 92%, while medium and complex queries achieve 85% and 78% respectively. Overall, the system reached 85% execution accuracy on the first attempt, proving that active exploration can outperform static embedding-based methods in real-world scenarios. So, when should you use SDE-SQL, and when is RAG a better fit? RAG is ideal for situations where speed and cost are more important than absolute accuracy. Think high-volume, simple queries on well-documented schemas. SDE-SQL shines when accuracy is critical, such as in analytics, compliance, or complex multi-table queries with dynamic or poorly documented schemas. For many organizations, a hybrid approach works best. Route simple queries to RAG for speed, and send complex ones to SDE-SQL for accuracy. Despite its strengths, SDE-SQL has some important limitations. First, latency can be an issue. Queries may take 7 to 20 seconds, which is too slow for real-time applications. The cost per query is also higher, and running multiple probes increases database load. The system relies heavily on well-crafted prompts, and it can't learn from past successes or failures. Future improvements may include reinforcement learning to make the exploration process more adaptive and efficient. Building this SDE-SQL system taught me that sometimes the best solution isn't adding more infrastructure, it's using what you already have in a smarter way. SQL databases are incredibly fast at answering queries, so why not let the AI ask questions before generating the final answer? By letting the language model actively explore the database, we achieve higher accuracy and adaptability, especially for complex, real-world scenarios. While SDE-SQL won't replace RAG for every use case, it's a powerful tool for anyone frustrated with the complexity of vector databases and embeddings. Sometimes, the best exploration tool for a database is SQL itself.